Messengers of space, instruments in the universe's symphony, bearers of the movements of spacetime. Gravitational waves are the target of our attention today. While electromagnetic waves are seen by astronomers from mostly weak gravity, low velocity regions because strong gravity regions are surrounded by thick layers of matter that prevent the passage of these waves. Gravitational waves come from regions in space where gravity can only be described by Einstein's theories and where matter moves nearly as fast as light. However, gravitational waves are neither scattered nor absorbed by matter, as are electromagnetic waves and neutrinos, which, for example, are easily scattered in the core of supernova explosions. Gravitational waves, according to Einstein, are ripples in the fabric of spacetime that move in the speed of light. According to Tutor, co-founder of LEGO, gravitational force of a gravitational wave is proportional to the particle's mass, whereas the electrical force of an electromagnetic wave is proportional to the particle on which the wave acts. And as all particles have mass, all particles experience the effects of a gravitational wave. Cosmic gravitational waves are emitted by large-scale core implosions of huge amounts of matter, like the implosion of the core of a star, or by large-scale core pulsation of the space-time curvature. For example, the pulsations of newborn black holes. Gravitational wave astronomy is revolutionizing the way we study and understand the universe. The main reason is that, with the study of gravitational waves, we may be rewarded with major surprises, as well as extensive information that cannot be acquired any other way. Gravitational waves are the most recent proof of Einstein's gravity, as well as further verification of black holes, which are the most unwelcome parts of his theory. Apart from that, verification confirms that gravity propagates at a certain speed, for if the speed was infinite, there would not be the formation of waves, but only an instrument to define absolute time for all the universe. Substantial information, such as the source's celestial coordinates, the source's nature, and details are all carried in gravitational waves. This can all be extracted the following way. The detector will evaluate the source's right ascension, declination, and waveform, which will lead to the source's celestial coordinate. After that, the source's nature will be studied using the discovery of which, if any, source of electromagnetic waves produce the gravitational waves. These discoveries will be crucial for better understanding gravity, for example, as Darn explains, by the comparison of the arrival times of gravitational and electromagnetic waves from the same sources. According to Aranha, MIT professor and inventor of the laser interferometric technique, an interferometric gravitational wave detector acts as a transducer to convert these space-time perturbations into a measurable signal. In September 14, 2015, the advanced LEGO detectors received a gravitational wave signal determined to stop the world. Going from the equivalences of two black holes, the detection launched the era of gravitational wave astronomy and revolutionized the way we perceive the nature and dimension of our universe. For what happens in enormous scales affects us here on Earth in the tiniest of proportions. This video is presented to you as part of my TCC project on gravitational waves.